I'll be talking about a system that we developed to help blind people. And more specifically, we want to prevent head injuries because it's actually a pretty big problem for blind people. So a survey done in 2011 shows that 19% of legally blind people report that they have more than one head injury per month, which is quite a lot. And about 55% say that they have at least one a year. And actually, one of the biggest problems there are overhanging obstacles, like tree branches hanging into the road and stuff like that. And the problem here is that you can't really detect that with a white cane, and even guide dogs aren't that helpful in that case. So our proposed system looks something like that. You have a wearable camera on your head, because it's obviously a good place to put if you want to detect head obstacles at head height. And it provides a video stream. We calculate the optical flow, which tells us how parts of the image are moving over time. Then we calculate the focus of expansion. That's the main novel new thing about that method, because we calculate it in a probabilistic fashion. And that tells us where in the image the camera is moving towards. And then we are calculating the divergence, which corresponds to time to contact, and above a certain threshold we warn the user, basically. So the focus of expansion, as I said, is a property of an optical flow, and it basically is the point towards which the camera is moving in the image. And it's basically characterized by all the motion vectors are pointing away from that point, right? So that would be the red point here, would be the focus of expansion. Ideally, if you have a perfect noise-free optical flow field, then you can just determine that by triangulation. You just take two vectors and can triangulate directly the focus of expansion. In reality, that doesn't work. So what we're doing is we're taking samples of vectors, of vector pairs, and do that a lot of times, and it basically gives us a probability distribution of the focus of expansion. And it looks something like that. So that would be for an optical flow field which has very low noise, and you can see that basically the focus of expansion is very finely defined here. If you increase the noise, then the variance increases basically, and if you have a lot of noise, then basically the measurement is not useful anymore. So basically, that method does not only give us the point of the focus of expansion, but we also get a variance, a measure of the quality of the method of the measurement. And so when we determined the focus of expansion, we are fitting an affine motion model to determine the divergence. And what we are doing here is we are using the variance or the quality of the focus of expansion that we gathered to also filter the divergence. So basically, our idea is if the focus of expansion is not very well defined, then probably the divergence will not be very useful as well. And we are basically just discarding everything, right? So if the focus of expansion has a very high variance, we basically just shut down the system and just don't warn the user of anything. And the results look something like this. So you can see for the same video sequence, three methods. The one on the right is ours. One method is we just assume that the focus of expansion is in the center of the image, which doesn't really work that well. Another method to determine the FOE is the counting method, and you can see that works. But the problem is that since you have a lot of head motion, you have a lot of divergence that is basically just noise. And on the right side, that's our new method. It also works quite well. But if you see at the big picture, basically, we can filter out all the occurrences where the divergence is basically just noise, and we get a very clean signal that an obstacle is approaching. If you want to know more, please visit me at the poster session. Thanks.